Good morning, welcome everybody to this talk. Actually, this talk is going to be more of me just rambling on for an hour and 15 minutes. I will not be disappointed if you all just decide to walk out, so don't worry. Make yourself comfortable, this is Las Vegas. Okay, so before I begin, quick introduction to this talk. If you're going to refer to the slides in this talk, don't. I pretty much whacked off 80% of the slides. I figured I'll spiff off the contents. The theme is going to be the same, but I thought, to Pluto with the slides. I've been teaching a class for the past 4 days. I've had enough of slides, and some of my students here can attest to that. So I thought I'll just do demos and show you stuff by doing stuff instead of talking about it. All right. So, quick introduction. Who am I? I am Saumil Shah. I am the CEO of a very small company called NetSquare Solutions, who does security stuff, blah, blah, blah. We're based in India. Okay. That's me. Why did I get into buffer overflows and Metasploit? Well, I used to be doing web stuff for the longest time. My personal belief is, although on the application space these days, with managed environments coming up, we're seeing less and less of overflows. There's still a huge potential for buffer overflow conditions to exist in legacy code. Also, what I feel is there's a whole lot of embedded systems coming up. There's processors everywhere. There are vectors to these processors everywhere, and I'm sure there's going to be a lot of overflows in such embedded systems. ARM, Freescale, MIPS, you name your favorite embedded processor, because crappy code still exists. People still code using Google. That's why we all have jobs. That's why we're all here, right? Okay, so that's why I got into buffer overflows, and I figured, why don't I just do a quick talk on how to use the Metasploit framework for doing R&D with buffer overflows. Back in the day, you pretty much had nothing to help you code up buffer overflows. The only thing you had at hand was VI. That's about it. But things have changed. You have a very powerful framework called Metasploit to help you play with overflow vectors, choose shellcode, get encoders, all that fun stuff. How many of you have worked with Metasploit? Quite a lot. I'm not going to rain on HDM or SpoonM's parade. I'm going to still stick to 2.6 for this talk. Those guys, I believe, are releasing 3.0, the beta version, later on today. I'm not going to be sticky about specific versions of Metasploit. 2.6, 3.0. What I'm going to talk about is, how do you plug in your own exploit into the framework? And, how do you make things work with the framework? And then how do you get the framework to choose shellcode for you and things like that? So that's what we're going to see. Quick overview about buffer overflows. Buffer overflows is the situation when you're trying to stuff a large chunk of data into a container that doesn't have enough space. What you do is trying to pour water in a cup, and it spills all over. Spills over the memory, screws up everything, and it does stuff, and somehow you get a shell. So that's a typical situation. We've all done that. Thanks. Okay. And if you take code like this, for instance, buffer 128 string copy argv1 into buffer, classic error situation. If you have command line argument 1, which is more than 128 bytes, this program is going to puke. It's going to throw up core. You get segmentation fault core dump. And then for guys like us, core is music to the attacker's ears. We'll use the core file to do post-mortem debugging, figure out what caused the problem, take a look at the registers, and then begin the whole process of exploit development. Right. For this session, this is actually more like a tutorial session. I'm going to cover 3 examples. I'm going to cover one example of a classic Unix Stack Overflow on Peercast. Then I'm going to cover Oracle 9.2's HTTP interface. And time permitting, there's a new SIP library out there on Windows, SIPXTAPI. and there are a lot of SIP phones making use of this free library. So we'll cover an overflow situation on that. I mean, the idea here is not to educate you about how those overflows happen, but how can we plug in our research code into the Metasploit framework and get these exploits integrated into Metasploit. Right. Okay. So quick overview about the internals of things. This is the x86 CPU register map. You have 4 general purpose registers: EAX, CBX, CCX, CDX, which pretty much like your variables ABCD. You have 4 pointers: the stack pointer, base pointer, source index, destination index, and lastly you have the most popular register of them all, right? We're all in a quest for EIP. Any which way we can get EIP equals 41414141, you like say yes, go for it. Actually, if any of you guys like making cool t-shirts, I have a request. I just want a black t-shirt which says EIP is equal to 0x41414141. Count my first order in, $29, I'll pay for that. Okay. Now, just a quick introduction about Stack Overflows. I mean, I know quite a lot of you would know this. It'll be elementary stuff. But I just want to make sure everybody in this room who still ends up staying here is familiar with this. Thank you very much, sir. Excuse me while I plug this in. I don't want to get fried by completing this. Excellent. Okay. So here we have classic process memory map. Do I have a laser pointer? No worries. Okay, over there in the dark blue region, you have the code that is loaded up from the compiler. Your process is loaded up, all the code goes there, the compiled stuff. Then down below begins the heap. I mean, heap grows from the top of the memory down. That's where you get all your malloc memory. From the bottom up, you have the stack. And the stack is used by the process to push stuff on it and pop stuff off it. Whenever a function is called, what happens when a function is called? Just a quick refresher. Program control stops where it is, saves some stuff on the stack, jumps off to where the function is, does stuff in the function, and then how does it know how to get back to where it left off from? Well, the stuff it has saved on the stack is actually a copy of the EIP where it left off from, rather specifically where it needs to resume to, and a copy of the previous frame pointer, the frame of the previous function. So when the function terminates, this is what's happening. When the function is invoked, you get your parameters pushed, you get your EBP, EIP pushed, the instruction pointer copies. When the function terminates, all the stack is cleaned up, and the copy of the saved EIP is retrieved and populated back into EIP. Cool, so far so good. So here's what happens if you have a function which is trying to dump a string into a 128-byte buffer. This is how your stack is going to look like. The frame 0, which is this light bluish region, has a local buffer on it of 128 bytes. And right immediately below the buffer, in the stack space, is a copy of the previous frame's EBP and a copy of the saved EIP. Now, if you try stuffing A's into this buffer, what's going to happen? We're going to overrun the buffer and end up overwriting copies of the saved EBP and EIP. When does it mean, question, does it mean at this point we have control of EIP? No. When do we get control of EIP? When the function returns. So, I mean, supposing you did this and the function never returned, you still don't get any love back. Only when the function returns is a copy of the saved EIP popped off, and what gets loaded into the actual EIP is what you overwrote it with. So this is your overflow situation in a nutshell. And if you do GDB or WinDBG, you'll get register values like this. EIP is 41414141. We also sometimes end up overwriting EBP. Right, so this is the buffer overflow situation. Now for all exploit development, I mean, this is actually when a vulnerability manifests itself into an error situation. Now begins the whole process of making it work. By making it work is, we're not just interested in crashing programs, are we? We want shells. So now how do you get stuff packed in to this and make the program do tricks that you want it to do? So we need to now answer the question like this. We need to somehow control EIP. Where the two things we need to do is, we can take control of EIP. We can stuff EIP with whatever 4 bytes we want. Question is, where do you want to go today? Right. Then, if you know where you want to go to, can you inject your own code in that location? And the third is, what code to inject? So once you find the 3 pieces of this puzzle, you've got a working exploit. Simple? Okay. Now there are many ways of snatching control of EIP and you know, putting your code in the buffer and jumping to it. We don't have time to cover all, but I will cover one classic situation called jump to register. This is actually a very, very reliable way of exploiting Stack Overflows. You don't need a lot of guesswork. Here's the situation. Now the top diagram is actually the stack on its side, sleeping. Okay. And you overwrite it with the buffer. You keep on overwriting it until you run into the region where EIP was saved. That's that dark blue region, overwritten with that yellow region. Right. It's amazing. And thank God I coded it with colors so I can, you know, narrate without a laser pointer. Right. Now when this function returns, more often than not, you will have some register or the other pointing to a part of this buffer. Why would a register point to a part of our buffer? Well, the answer lies in, when you generate code with an optimizing compiler, a lot of times release code or production code is generated with optimization for speed. Try to keep as many values immediately available in registers as far as possible, rather than loading it from, looking up a symbol table, loading it from the memory and then pushing it back to the memory. This avoids a whole lot of memory transfer. So if you've got optimized code, chances are that at the time of the overflow, you'll find one of the registers pointing to somewhere in the buffer. Maybe it's done a block copy of the part and it's pointing halfway through when it died. Maybe it's about to copy something. Maybe it's pointing to the very beginning. Maybe it's pointing to the very end. You don't know. But we can find out all this stuff from analysis. So, assuming in this case I have the example that EBP points to somewhere within 4 bytes of the beginning of our buffer. Now comes the whole idea of exploit construction. What we're going to do is, we're going to pack our shell code near the beginning of the buffer, but avoid the first 4 bytes. Then we're going to figure out some mechanism of jumping to where EBP points to. In our instruction set, especially on x86 CPUs or a whole lot of CISC CPUs, you will